So we're on to Schrödinger's equation. All right, so Schrödinger's equation, it's a scalar second-order differential operator that acts on a wave function. But even though it's second order, it's actually only second order in terms of its space part, and it's only first order in terms of its time derivative. And believe me, people understand this. Okay, they describe it that way in graduate level physics books. So we're not putting a big surprise. We are going to rearrange the furniture in the house. That's essentially all that we do in this exercise. But again, I think the results look prettier. Now, since prettiness is a judgment call, I'm going to put that equation down at the bottom of every one of these slides, and you decide at the end whether you think it's pretty or not. Okay? All right. So, so there is the actual animal. It's got these factors of I. It's got a del squared. It's got one time derivative. Okay. And so the first thing I do is I drop all my factors of I. And then I say, well, that's really a scalar operator because time derivative is a scalar operator. Del squared is a scalar operator. Believe me, people know this. But this is, again, part of my let's write everything down. Most people would say, I've got a scalar operator. I'm not going to bother you with that zero with an arrow over it. Okay? I understand them saving some chalk, some ink, but to me, I want to see it, okay? Because it tells me that if I want to generalize this equation a little bit more than it is right now, I can act right there. I mean, there's no question of where I do something. It's sitting there on the page. So again, one of my odd things is I always write my zeros. So we're going to have a couple sidebars here. The first one is that we want to make a Laplacian operator as quaternions. And so all you have to do is really square one of those. But you get the curl of a curl. Okay? And it's actually not relevant to the Schrödinger equation. But it's nice to know that anytime you see a Laplacian, in the back of your mind you should go, you know, there's a curl of a curl over here. I know you don't want to look at it because it's scary, but that's too bad. I bet nature uses that. Okay, so now we've got to get to one time derivative using two operators, and by golly, that should be easy. Just one times the time operator, and that's it. So now we take these two observations, and we want to take that scalar operator and write it as two operators. And so what we see is a full derivative operator. We've got the dt time and then the del thing, okay? And then the next one, it's unity. Oh, unity, that's got to be dimensionless. And we've got this del thing. We can actually tell right away that this must no longer be like fully relativistic because, you know, one is a constant, okay? Okay, so that's all well and good. So now let's see, where do we go from here? All right, let me just stay a moment longer on this one. So can we see what we need to get? We can see we get the time element out of there. Well, apparently, oh yeah, I've got the scalar. The scalar thing says I'm not going to think at all about the vector part. But that means there's probably more that we could know or something. There's more calculations that could be done if we didn't put that scalar constraint on it. But since I'm trying to get a scalar out of it, it's pretty easy to read. Okay? It's going to be the dt of phi. It's going to be the second order spatial derivative of phi. It's going to have an hbar over 2mc. And that was actually fun seeing that that's a dimensionless number. Hbar over mc. So that's a momentum. And so that's going to be. All right. So I want more cowbell, I want more hbar. So you can actually wipe out my units if you so choose, and then actually go ahead and throw it an hbar across the way, and you'll end up with the right units. Okay. See, since I wrote g hbar over c5 on both sides, I mean I can just wipe that out, and if I multiply through by hbar, yeah, it's spot on. So that's pretty good. All right. So I think that's it. I think that's it. That's my way of writing the Schrodinger wave equation using quaternions, using dimensionless operators. Oh, and there's that line. Nature nurtures naked numbers. It might make a bumper sticker someday. Who does? All right, so now we're going to move on to relativistic quantum mechanics. All right, 2.6, Klein-Gordon. All right. All right, so we're going to get the Klein-Gordon equation out of here. It uses both time derivatives, and we're actually going to write out the phase, even though I'm not sure if it's actually used currently in standard physics or not. This is my own issue. This is the most famous equation of all. I wrote it so big because, I mean, this really reaches out into the popular culture. You see it included in the artworks and that sort of thing. But I actually think it leads a physicist a little bit astray. One of the things, a little cultural element, Einstein's manuscript where he first didn't write this was put up for sale, and it didn't meet the asking price, which was, I think, about $4 million, because what he wrote down was E equals mc squared over the square root of 1 minus b squared over c squared. And people were like, well, we don't, you know, that's not equally mc squared. There's that part I don't understand. Even less than E equals mc squared. I actually think that maybe that's the most important part of the equation. But anyway. So people emphasize this equivalence, and certainly physicists know the real correct relationship. I shouldn't say the correct relationship, the more general relationship. E equals mc squared for only one inertial reference frame you can come up with. And it's not generally true. You know, if you're walking by somebody, you're going to have a different opinion about that. Not very different, but different nonetheless. Okay, so I want to only work with equations that are always true. So what I do is I square this for momentum, and you get that E squared minus P squared, and you get that M squared C, the fourth thing. And this is all I ever use. Okay? And this, again, makes me rather odd. Okay, people are so at peace with E equals mc squared that you know, just choose a frame where P equals 0. It's like, no, I won't do that. Because if I choose that reference frame, somebody else can choose another, and it won't quite be true. And the other thing that is just, to me, the huge elephant in the room is that when I do it this way, I get this 2EP times C. That's a perfectly valid thing, okay? It's not like I've broken a math rule or something. That should be relevant with doing these calculations. And I don't think that people use that. I mean, it doesn't even have a name as far as I know. If somebody actually knows of its name, you know, please tell me, and then I'll be able to read up on it. But I don't see it in the literature, energy times momentum. Okay, so we've got to have a couple sidebars again. We're going to convert numbers, the numbers E and P, to operators. Okay, so this is, again, another little indication that we're not quite in classical quantum mechanics. where we had one was a number, the other was an operator. Here, they're both operators. Okay. And then sidebar number 2 has to do with four momentums. That you can rewrite energy and momentum as this factor gamma. M times gamma is energy, where gamma is the square root of that factor that showed up in Einstein's original manuscript. And then gamma beta is the velocity times that gamma thing. All right? And so if you square this, what you end up with is you get that gamma squared times 1 minus beta squared. Well, hold it. Gamma squared is also 1 minus beta squared, so that's just unity. It's like, oh, that's another reason why this is such an important relationship. We see unity in it. Unity is good. Okay, so now we substitute this all in, and we go through this kind of process, and we say, okay, so I get two time derivatives, I get two space derivatives, and I get a time and space derivative. That's the energy momentum thing, and so that's just kind of rewriting things. And now I divide through by m squared, and so this is my completely dimensionless expression. And here my phrase. I love nature's naked numbers. You see, I've got a real genuine 1 over there. Okay, I also have gamma squared beta in the phase. But I've got this time derivative, second order time derivative. I've got this h bar over m. Well, this time it's h bar over mc squared. So that's similar to what I saw in the Schrodinger equation, if I recall. And now, is this Klein-Gordon? Well, actually it's not. Because there's a sign difference because of the way that standard physics writes things. They throw in factors of I, the ones that I threw out. And so that's what it would take to make it more like the standard equation. So now you at least know a way to derive the Klein-Gordon equation, which shows up in quantum mechanics. All right.
So again, you're only looking at the scalar part as the Klein-Gordon equation, right?
Yes, absolutely.
The vector part, does it mean something?
I think it should. Okay. Have I done any calculations with it? No, I haven't. Okay. I haven't seen the consequences of it. And I am not enough of a student of real physics, relativistic quantum field theory, to know whether they use that. It hasn't come across in my readings. Everybody's just like, here's Klein-Gordon, or I've decided to use Dirac. And, it's like, it doesn't come up. It's kind of like structurally it can't come up because of the tools that they're using. So I'm thinking that they don't work with it. They might, well, that's where I stand at this point on that issue. All right, so I think we only have one more collection of slides. I am only subjecting you to half as much brain damage today as yesterday. All right, so let's see. All right, so the Dirac equation squared ends up being the Klein-Gordon equation. And that's only kind of roughly true. It's not formally for all orders, but it's roughly what's going on. And so in a hand-wavy way, this is the Dirac equation on top. I haven't told you what A and B are. Alpha and beta. I haven't told you what those are. But you can see if we squared that, we should get two factors of time derivatives. If we square that, we should get a couple of del operators in there. But, we get an m squared out of that thing if we divide through by h bar, but this is all real hand-wavy, because I haven't said what alpha and beta are. Okay, so I'm going to see whether I can get to something that looks like Klein-Gordon and where things work and where they don't. Okay, so what I'm going to do is collect space-time terms together. I'm going to drop all factors of I. Okay, so now I've got a time derivative and a del operator. Okay, and I don't have any factors of I. So that step was pretty simple. I'm going to make this thing dimensionless by putting the beta on the other side. So I put that over there. And, oh, but I'm really kind of really rearranging things a bit. They usually put the beta right next to the mass. And I'm saying, well, if I've got an alpha, this is a bit hand-wavy. Sorry, it's just the nature of the way I was operating at the time. Since that's just a scalar, I'll make up a new beta and have it multiplied by time. I'll have to, do something to make sure alpha doesn't get too upset, and look at it that way. And then if I just tried to think about this without those alpha betas, okay, this is what I would have. I would have an h bar over mc squared del phi. Okay, that looks pretty easy. If I square that thing, I'm going to probably end up right at the Klein-Gordon equation. So that's why that's good. Okay, so I'm going to talk a little bit about spin 1/2, because that's what makes this difficult, is spin 1/2. And what I'm going to argue is that we should embrace it and not fear spin 1/2. So a beer in the hand, let's say I don't really have a beer, so why don't we just use a camera in here? Let's think about 2 pi symmetry. So if I've done my deed, I will come back to exactly where I started from, and this is 2 pi rotation. I could do a cartwheel if I felt more energetic. I could do a backflip. I've got three different ways I can do this. Okay, that was all example of 2 pi symmetry. I will same camera. I'll show you 4 pi symmetry. Because now I go with one twist around, and am I back to where I started? You've seen this trick before. I have to do it again. That's an example of 4 pi symmetry. And why is this different? It's the same camera. It's the same hand. Okay, the reason is I got a shoulder here. It's connected. Okay? And I think in a way it essentially constrains one degree of freedom in space. So now space is not the same, okay, because of my shoulder. It's saying I basically have one constraint on it that I don't have when I'm doing here. My shoulder isn't a constraint there. So that is an example of 4 pi symmetry. So if 3 space somehow gets split into 2 and 1, there's the dimension with my arm, and then there's the other thing. That's when I think 4 pi stuff begins to happen. All right. So, oh, great. And sidebar number 2 are the gamma matrices. Now, this is going to be a longer sidebar because the gamma matrices are the things that make up the alpha and the beta. Okay. These can be manipulated if you're in graduate school without really being understood. Okay, you can look them up. You can do gamma 1, 2, 3, 4, 5. These kinds of things. They have these types of rules, but you can't really explain it to mom. What is going on here? Yes, math is happening. Okay, math is happening. You can apply it to this. You can solve a problem. It's great. Okay, it's just what's going on. That's a good question. So it's one nice thing about owning quaternions.com is that people all over the planet, if they do a little bit of research in quaternions, they sometimes stumble over my work. They communicate with me. And so there's an engineer in Mexico, and he said, that the 16 gamma matrices that map to the 16 quaternion triple products. I was like, really? I mean, that at least can be summarized quickly, right? It's like a 1 I, j, k on one side, 1 I, j, k on the other, multiply them through. Oh, 1 times 1 times, hey, that's going to be the same. But what happens when you start doing some of these permutations? and find the one permutation that makes sense. We've got A, where you start with Tx, Y, Z, and end up with Tx, Y, Z. Whereas in B, if I just hit it on one side by a factor of I end up with minus x, t, z, minus y. So what this little operation does is say, whatever measurement for time that you used to have, consider it now a measurement of space. And that measurement you made of space, now consider that going in the past in the value of the x direction. It's like, that's really crazy. And don't think of that measurement of y as being a measurement of y anymore. Put it over in the z slot as long as you take the mirror reflection of what's going to happen in the y spot. And the same for z. It's like z is no longer z. Z is now sitting in the y spot, and it's just looking like an old self, except that it's y. It's like, you've got to be insane. I mean, these are not complicated operations, are they? I mean, it's just, these are triple products. These are the simplest triple products that can form, but they're wacky. So if you hit it on both sides by at least the same letter, J and J, what it does is it takes it from some time in the future to its mirror reflection in the past. To its time in the past, and the mirror reflection of y, but not the mirror reflection of x or z. Okay. And now if you hit it by a k and a j, everybody ends up being negative. We get time going where space should be. We get x going where y should be. And it's like, wow, that's pretty insane. Remember that sum of all possibilities, all possible histories? I think what that means, in effect here, is that we really are messing with time and space in every possible way. And so this is very, very odd. It's like, so why is quantum field theory so hard? You know, why this Bohr's argument that it's just impossibly difficult to understand? This might be a nice concrete reason why. I mean, I don't like my time going into space. I don't like my space going into my time. But if this is a way to represent gamma matrices that show up in the Dirac equation, which show up in quantum field theory, well, that would be a nice concrete reason why. So this is just a little sampling I'm going to provide of the talk tomorrow. And I need it to make this whole discussion of gamma matrices much more concrete. Okay, so this is the one animation I have. This is software that I wrote that completely makes sense to me. And it's funny, but ironic, but it's about the only one that really does. But the idea is that I have a pile of quaternions. When I mean thousands of quaternions. I sort them by time, and this is a 10-second film, a specialized 10-second film. And depending on its time, it shows where it shows up in the animation, and where it shows up in X, Y, and Z. I use something called point of view ray to draw the 3D thing. So we have the animation is front and center, and we have 3 complex planes. The reason I drew the complex planes was I found I couldn't think about the animation very precisely because our brains really are bad at thinking about video. But still pictures we're much better with. So you can see that the first complex plane is t versus y, so you can see it goes up. This one in the corner is time versus z, so this is going backwards into the screen. The third complex plane is x, so is it going left? It's going from the left to the right. Okay. Now in the upper corner is basically a summation of every single possible state that yellow ball is in. Okay, I mean, I literally, on a software level, I merged them. Okay, the images. And so to me, actually, that might be the wave functions, which is supposed to be, this has all the information in it, is kind of what people describe the wave function as. And then I'm doing random sampling of that. And if I do enough random samplings of it, it would recreate exactly that same thing. I think in my 10-second video, actually, there are lots of places I don't get to, but that was a limitation of GIF software. And that's what I use here. Okay, so this is quaternion addition. What I did was I started with one quaternion value, and I kept on adding the same thing over and over and over and over and over and over again. And I think you can agree that looks like an inertial observer. They're traveling at a constant velocity. But what's like, to me, profoundly cool here is that the most basic operation of quaternions addition leads to an inertial observer, which is at the base of special relativity. Okay. Now, I think, yes, now we're going to try and understand what gamma matrices are. Okay, so what did I do to make this? I told you. All I did was I multiplied by all 16 possibilities. Okay? I took that inertial observer that was traveling the straight line, and I said, let's say I've got 1,000 such points. For every one of those 1,000 points, I'm going to multiply on one side by 1 and the other side by 1. Oh, I end up with the same thing. 1 and I, 1 and j, 1 and k, 1, no, that's it. I and 1, I and j, I and k. You get 16 of them. And so when you see this, you go, okay, so what's kind of happening is I've got 4 clusters of 4. I can actually kind of see or sense the 16ness of this sort of thing. And so now I kind of, yeah, so there are four little balls coming in from 4 different corners. And so when Feynman says, well, you must do the sum over all possible histories, and you hear that there's these gamma matrices, and then I say, well, there's a way to do this with quaternions with all 4 permutations, triple product-wise. It almost starts to make sense. Almost. I mean, I don't claim that I'm just totally at peace with this. But what I'm saying is I feel like I've taken a very concrete step towards appreciating kind of more of what the gamma matrices are actually doing. So the trivial, quote-unquote, trivial Dirac equation is not a triple product. Okay, so if I square that thing, then I end up with, and squaring is okay for quaternions. I mean, there's no problem with that. You see that, oh, gee, I did end up at the Klein-Gordon. When I started this exercise, I said, well, you can't really square because I haven't told you what alpha and beta are. Well, now I have told you. I'm working with quaternions, so squaring is a legal thing. I haven't broken any of the math rules. There was no hand waving, and I get to exactly the Klein-Gordon. But you say, well, you got 16 others to work with, don't you? And it's like, yes. So if I go ahead and do those, then, well, look at that. I actually get the same scalar, which is good, okay? It's just that now the phase is different. And as I say, you know, I don't read people working with phase directly. I haven't read that. But it's kind of cool that now we have, it's not exactly the same thing. And maybe that's relevant. I just want to say that quaternions in no way make quantum field theory simple. But I'm feeling like this is a good and interesting and productive step forward. And so that's kind of one of the main things that I'm doing research on these days. So we'll end with a comic strip by Lowell here. It says, now the SUSY algebra closes off shell if we use the auxiliary fields, or better known as the Augie Doggies. Arg, this doggy. I would like to chime in, please. Yes, SUSY is unnecessary. And that, in fact, is one of the messages of my work, is that I don't think all these super partners are necessary. I don't think they will be found. And I just to understand the nature of the T-shirt and the research project itself, we are going against LHC. If LHC finds the Higgs, you'll be able to say, wow, I got this weird artifact from this weird guy that said there shouldn't be a Higgs boson. Okay, whereas, and if they find SUSY particles, the same story. My proposal collapses. And I'm at peace with that, okay? But if 2 or 3 years down the line, they say, we still haven't found the Higgs, and the modification they'll say is, we haven't found the Higgs, and we're 99.2% confident that the Higgs isn't within this range. That's how they talk. I mean, these guys are impressively precise folks, okay? There are already people who have said, you know, if we don't find the Higgs, that's going to be exciting because it means we've got to do new physics. And they don't know where they're going to do their new physics. I mean, they know they would have to do something, okay? Well, then you can show them your T-shirt, that sort of thing. And maybe strike up a conversation. But those are very concrete aspects of this work. So I think that concludes day number 2, and congratulations! Oh, all for making it.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
All right, so what are my qualifications for being able to do a new unified field theory? I must have pretty impressive credentials, right? Well, at MIT, I was a 4.0. And I think most people would be really impressed with that, because MIT is really a difficult place, except that it's on a 5-point scale. so you guys probably know I wasn't an A student. I was actually straight B, okay? But if it were for you kids just starting out, these are my real degrees, and I didn't have just one, I got 2. So you say, well, these must be very relevant, okay? Bachelor of Science in Life Sciences, Biology, that's not mathematical physics, and this one, Chemical Engineering. Oops. These were supposed to be, you know, 7, 18. No, I said 8 and 18. No, man, maybe I got it. Maybe I should just erase that and they'll pen something in. No, that'd be wrong. That would be wrong. Okay, so let's see. Is there something else that might impress you? Well, I was out of work for like a year and a half. See, I like to deal with big abstract things, not like concrete things like making money. So I have a couple stretches of long unemployment where I was thinking about stuff and wasn't bothered by the real world. My wife was bothered by that. But anyway, so I decided I would take the United States Postal Service exam. And this turns out to be a very difficult exam because it's not testing your knowledge of anything. It's actually testing a bunch of little monkey tricks, mental monkey tricks. Like how fast can you spot errors in addresses? How fast can you memorize 5 addresses and then recite them over here? And I got a study guide, and I learned that in those questions they had 4 numbers, and always the second digit was different. And even though I knew this little secret trick, it wasn't until like 3 days before the exam that I figured out a way for my brain to remember it. Like if it was a rising collection of numbers, I'd say Elm Street, Main Street, going up and down. And I'm one of the very few people you will meet in your life who got 100 on the United States Postal Service. So you say, well, I'd like to see your Postal Service uniform. You can't, because they have an interview process, and I failed the interview. And he's like, how can you do that? And I was like, well, because, you know, they said, well, what if you have a conflict with your boss? What if you have a conflict with a customer, okay? What are you going to do? And I said, well, I said the same thing. I said, I'm going to tell them that there are laws against having concealed weapons on your person, okay? And there are people who break those laws. That's not me. I'm not saying that. I'm just letting you know that there's some... No. I actually thought I gave rational answers to this thing. I really don't know why they did that. But I am not a Postal Service... I'm the one Postal Service person who got 100 and failed the exam. Okay, so... oh, yeah, so... So you say, am I really crazy or something like that? And it's like, no. We far prefer the word certified, okay? I don't know if you're familiar with these kinds of things, but there are people who the state determines are, what is it exactly? Gravely disabled, or dangerous, yeah, I'm gravely disabled, I don't know. But this is my official certification. So please do not call me crazy. Call me certified. I'm official. Okay, anyway. So that's my one piece that says I am certified enough to maybe have come up with a new idea like this. All right, thank you very much.
Oh, yeah. Yeah, you didn't go postal.
Yeah, that would be a danger to others. That's a checkbox.